Good evening, everyone. Welcome to the seventh discussion hour of this course on robotics. In the last week, discussions are we discussed about the static force and moment analysis for serial manipulators, and we saw how joint torques are related to forces and moments acting on the end effector when the joints are locked. So basically, the manipulator acts as a structure. So there were some network issues on my end, so that's why the meeting started late. Uh, yeah, so I was just getting started with the content for this discussion hour. And in the last week's discussion hour, we covered the static force and moment analysis for manipulators, in which we saw how joint torques are related to the forces and moments acting on the end effector uh, when the joints are locked. So basically, the manipulator is not moving and behaves like a rigid structure. So there we saw how Jacobian appears in the relation between the forces uh, at the end effector and also the joint torques. Now, in this week's discussion hour, we will discuss the dynamics of manipulators. So, whenever we study about the dynamics of a system, we are concerned about the agency that is causing the motion of the system. So kinematics was just the study of the motion without being concerned about what is the agency or the cause of the motion. Statics is concerned with forces and moments, but there is no motion involved. Dynamics is basically in which there is motion of bodies, and we want to relate the forces and moments to the motion of the bodies. So basically, what we have is the cause or the agency. So something which causes a body to move, right? So those are the our forces and torques or moments. And the outcome is the motion, that is velocity or acceleration. So if, let's say, a rigid body is being pushed by a force F of mass m, and hence it is accelerated with acceleration x double dot, with x being the displacement of the mass from the origin. So then the well-known relation of F is equal to mx double dot. This is what we call as the relation between the agency and the motion. So this is called as the equation of motion for a rigid body uh, sliding on a frictionless surface. So it's the ideal scenario. Are you able to hear me now? Because hello, am I audible now? Hello. Hello. Okay. There's some issue. Hello. Can you hear me now? Hello. Hello. Am I audible? Hello, Satish. Can you confirm if you can hear me? Hello. Oh, okay. So, Ninad, I think there is some issue on your end, maybe. Okay. Yeah. So, let me just. Okay. So, let's continue our discussion. So, equation of motion is basically something which relates the forces and the outcome, that is the motion, represented by the acceleration. So, in the case of linear motion, it we have the well-known Newton's second law of motion for a point mass, that is F is equal to mx double dot, and similarly for the angular angular motion we have torque for a angular motion about a fixed axis. We have the expression tau is equal to I alpha, where alpha is the angular acceleration and tau is the moment about that axis. So these are the very simple equations of motion which we have encountered while analyzing simpler systems. Now the goal here is to basically, so what's our objective? So our objective is to derive the equation of motion for a serial manipulator. So equation of motion is something which will serve as the model of the dynamical model of the system. What is the dynamical model of the system? That is our equation of motion, EOM. I will use this abbreviation from now on. And so basically since we are considered about dynamics now, so the mass and inertia of the individual links come into the picture. So those are called as, earlier we had seen the kinematic properties of serial and of these manipulators. We are just considered about the length of the links, because that is the only thing which appears in the Jacobian matrix. Now when we talk about dynamics, the dynamical properties come into the picture. That is the mass m and the inertia tensor, which will represent like this. And we should also note that this is not the the most accurate or the true model of the reality, right? So we have assumptions here. The first assumption is that the links are rigid, that is, they do not deform. And the second is that the second assumption we can like we can take away in several ways, but primarily this assumption stays throughout our discussion, is that the joints are frictionless and there are no losses basically. So ideal joints, no damping, no friction, nothing. They are ideal joints. So this is basically our, what we can say as a ideal rigid multi-body system. Rigid multi-body system. So ideal because we are not considering friction and damping of the joints, and all the links are rigid, and since multiple links are connected together, so it's a multi-body system. So basically it is this system which we are analyzing, and our goal is to find the equation of motion of such a system. Okay, so once we have set out the objective, a quick note about the dynamical properties. So mass is that is very straightforward quantity. It's not something which requires a lot of understanding to grasp. The other quantity that we encounter is the inertia matrix or the inertia tensor. So the inertia matrix, right? So this, and its elements are represented like this. So this matrix has some special properties. It is a positive definite symmetric matrix. So positive definite means that the eigenvalues the eigenvalues of this matrix are always greater than 0, right? And there is a physical significance of these eigenvalues and the eigenvectors of this matrix as well, which I will discuss in a moment. So, and the definition of these terms is given as that Ixx is the integral over the entire volume. So let's say this is the volume of this is the object, this is a 3D object, right? And this is the axis about which we want to compute the inertia. So first we take a small element, and that element is, let's say, placed at x comma y comma z, right? So then we can write these terms like this. So Ixx is y square plus z square and then rho dv. So what this means is that basically this term is the mass of that small element, mass of the small element, and this is basically related to distance terms basically, right? So similarly Iyy is written n, so this integration is over the entire volume of the object. So this integration is over the entire volume of the object. Similarly, the other components are calculated. This is Iyy and this is Izz. So Izz is something which will be commonly used in planar cases, and so these are the three diagonal terms. The off diagonal terms are calculated like this. So they are calculated like this, and like yz will be calculated like this. So you will see by using these expressions is that Ixy is equal to Iyx, Ixz is equal to Izx, and Iyz is equal to Izy. Now the representation of inertia matrix depends on the reference frame. So whenever you are using the inertia matrix, it must be specified that what is the frame in which the components of that matrix has been written. So, and the transformation of the inertia matrix can be done like this. So if I want to describe the inertia matrix in frame A, then, and I have the description in, let's say, frame 0, then I will use my rotation matrix from 0 to A like this, transpose. So this is how inertia matrices are transformed. Note that the order of rotation matrix here is also important, because if you uh, switch the orders, then the transformation will not be correct. So this is how, let's say, if I want to, there's a rigid body, and I can express the inertia in its center of mass frame, or the world frame, or there is a special frame that is called the principal axis. So principal axis, so when the inertia matrix is represented in the principal axis, the principal frame, then inertia matrix becomes diagonal. So for any body, uh, there exists a set of axes. So there exists a coordinate frame in which the inertia matrix can be expressed as a diagonal matrix, and this result also follows from a result of linear algebra, is that a positive definite matrix is always diagonalizable. So this also follows from the fact that a positive definite matrix is always diagonalizable. Okay, so which means that when the matrix is diagonalized, so the only non-zero terms lie on the diagonal, right? The rest all terms are zeros. And these values, I11, I22, I33, they are called as the principal moments of inertia, and the associated coordinate frame, like the coordinate frame in which the inertia matrix comes out to be diagonal, the associated frame is called as the principal axis. So principal axis depends on the distribution of uh, mass of the body that we are analyzing. So it is not something which which we can decide that this is the principal axis. It depends on how the mass is distributed. What we can do is that we can align, let's say if we are assigning some reference frame, that we can align the reference frames, or we can choose the principal axis as the reference frame if it is convenient, so that our inertia matrix becomes diagonal. And a bit of more in mathematical terms, these values turn out to be the eigenvalues of the inertia matrix, and these axes, they are the eigenvectors of the inertia matrix. Okay, so to summarize about the inertia matrix, so inertia matrix is a positive definite symmetric matrix. It also it also has descriptions in which it is completely diagonal. It's a diagonal matrix. That description is can be written if the frame in which the inertia matrix is described in is aligned with the principal axis. How can we find the principal axis? We have the inertia matrix represented in, let's say, any frame. Then we find the eigenvectors and eigenvalues of uh, of that matrix. The eigenvectors will correspond to the frame in which it is diagonal, and the eigenvalues basically correspond to the principal moments of inertia, that is I11, I22, and I33. So this is a brief about the uh, inertia matrix. How to compute inertia for different shapes is something which, when you attempt problems, you can just try out. We have the some basic theorems which we study in our high school, the parallel axis theorem, the perpendicular axis theorem. Those are also uh, applicable. Right. Now, moving on to our main objective, which was to uh, find out the equation of motion, the general equation of motion of an ideal rigid multi-body system. Any questions at this point, you can just let me know. Of an ideal rigid multi-body system. So there are two approaches. There are two approaches which we can take to derive this, and both are used. So what we have is, we have this chain of rigid bodies, and one is to basically use Newton-Euler equations for each. So we write the Newton-Euler equations. So we draw the FBD for each of the links, write the Newton-Euler equations for each of the links, and before that we'll also need to do the velocity propagation. And after doing velocity propagation, we write the Newton-Euler equations for each of the links, and then basically eliminate the variables to get the final results. So that is known as the Newton-Euler formulation. So this involves drawing FBDs and doing velocity propagation, and then writing the LMB and the AMB equations, linear momentum balance and angular momentum balance for each link. The other is what is called as the Lagrangian approach, or the Lagrangian formulation. This also involves velocity propagation, but does not involve this FBD and LMB and AMB. So velocity propagation, and then we write a quantity known as Lagrangian of the system, and then use the Euler-Lagrange equation to get the equation of motion. Euler-Lagrange equation to get the equation of motion. So today we'll first discuss the Lagrangian formulation, and we'll try to grasp that, and then if we still have time, then we can discuss the Newton-Euler formulation. So since so now we'll completely go into the Lagrangian formulation. So first thing to note here is that what we will discuss right now, it is applicable only for conservative systems. Like, it can be extended to cases where non-conservative forces are also there, but we are not going to discuss that right now. So right now what we will discuss, it is only applicable for conservative systems, that is systems in which there are no non-conservative forces that are acting. So basically friction and all is non-existent, which is covered by our assumption of ideal system. So let q and q dot represent the generalized position and velocity of the system. Generalized position and velocity of the system. So for a serial manipulator with all revolute joints, let's say, then it will be theta 1, theta 2, and so on, and q dot will be theta 1 dot, theta 2 dot, and so on and so forth. Then we have the quantity called as Lagrangian, that is defined as LQ q dot. It is a function of q and q dot, that is the difference of the kinetic energy and the potential energy. So for a body, the Lagrangian is the kinetic energy of that body minus the potential energy of that body. For the entire system, it is the total kinetic energy of the system minus total potential energy of the system. And so since energy is involved, it's called an energy based method, right? And all these are scalar terms. Now we come on to the Euler Lagrange equation. Something is wrong. So Euler Lagrange equation, and that is given as d by dt and then partial derivative of the Lagrangian with respect to the ith coordinate derivative minus dl by del L by del Qi is equal to Qi, that is our generalized force, and since here if all are joint torques, then it is equal to tau I. So this is the equation that we will use. The derivation of equation can also be done, but it is not in the scope of this course and this discussion R. If you are interested, you can read up more uh, on a field known as analytical mechanics. And mechanics, and you can take up a book by D.T. Greenwood. So the Euler-Lagrange equation, and if we leave out the derivation of this equation, then this is it, which is there in the process of finding the equation of motion. So basically, once we compute the kinetic energy of all the bodies, the potential energy of all the bodies, we write the Lagrangian, and then we do this for all I, with basically all the links in the system from 1 to n, and we get the n equations which formulate the equation of motion of the system, right? So the steps here are, the steps are: 1, do velocity propagation because that will be needed to write the kinetic energies. Then we write KEPE for individual bodies. Then we add, so you can write as KEI PI. So Ke is equal to sigma KEI, P is equal to sigma PI. Then fourth step is writing the Lagrangian as Ke minus PE, and the fifth step is for all I equal to 1 say n, we write that tau I is equal to d by dt del L by del q dot I minus del L by del qi. And finally, sixth step is we have the equation of motion. Right, so any questions still here? This is all pretty much straightforward. Okay, so now what we will do is that we will do this entire process of which I just described, these 6 steps. We will do this for a 2-hour manipulator, and what you will see is that although the process is very like straightforward, but it has it needs a lot of attention because many terms show up in the picture, and for systems more complicated than a 2-hour system, it's advised and it's practical to use computers and automatic differentiation like in MATLAB to get the equations of motion and not do it manually. So let's get started with it. I also suggest that while I do this derivation, I would be, writing some very long expressions, doing some differentiations and all. So I suggest or strongly recommend that you should also follow along when you watch this lecture or video, and maybe then you will be able to find out if there is a mistake on my end, or if you can follow the whole discussion much better if you follow along. So let's first again draw our beloved 2-hour manipulator system. I will follow the same notations as in the lecture slides, So, and this diagram is also a reproduction of that, so you can also follow from there, at least the diagram. And basically we will derive all the expressions that are given there. So the quantities that we need, first of all, theta 1 and tau 1 is the joint torque here. Here it is tau 2, the angle is theta 2. This is basically center of mass of the first link, center of mass of the second link, and we have the relevant quantities, that is mass of the link m2. Then we have the inertia along about the z-axis, so this is the izz term, and I will just write it as I2. Then we have the put the link length, that is L2, and also the position of the center of mass of the link along the length of the link. So basically the distance between the joint and the center of mass, that is R2, and the same quantities are written for the first link. And this is the y0 axis, this is the x0 axis, and gravity is acting downwards. Alright, I think we have everything to start. So let's follow these steps. So first is velocity propagation. So what the first is for link 1, right? Link 1. So angular velocity of link 1 is 0 0 theta 1 dot, that is link 1. Then the velocity of the first joint in the first frame, that is 0, because that frame is at that joint itself. Then we have the velocity of the center of mass of the first link in the first frame, and that is 0. And basically this C1 is the point, it is rotating with theta 1 dot at a distance r1 from the axis, so it is r1 theta 1 dot and then 0. So note that this velocity is written not in the base frame, that is not in x0 and y0, but the first frame, which is like this, right, rotating with the link. So as we have discussed multiple times now, that this left superscript denotes the frame in which that quantity has been written. Okay, now for I is equal to 2, we have the angular velocity, again trivial to write. Then we have the velocity of the joint 2 in the second joint frame, and that is basically L1 S2 theta 1 dot and L1 C2 theta 1 dot, and this is 0. So how did we get this? So again, this point is rotating with theta 1 dot, it's a distance L1 from the axis, so the velocity of this point is L1 theta 1 dot, and just that velocity is being expressed in the second frame. And finally we want to know the velocity of the center of mass expressed in the second frame, and that we can describe as the velocity of the joint plus the angular velocity cross with the distance. All right. So we can basically, since they both are in the same frame, we can write them and add them up. And here omega 2 has just the z component, and here it is in x component, so z cross x is z cross x is y, right? So this will be 0, then theta 1 dot plus theta 2 dot r2, and then 0. So this thing is L1 S2 theta 1 dot, L1 C2 theta 1 dot plus theta 1 dot plus theta 2 dot R2, and then 0. Any doubts still here? Because if you have doubts in velocity propagation, then you will have much more doubts going ahead. So just take 2 minutes, and if you are doing it on your own, then try to finish that. Okay, so let's again try to understand how to get. Oh, you are in V2. Okay, so V2, first let's understand what is V2. V2 is the velocity of this point, basically the joint 2. Okay, so in other words, it's the velocity with which this frame that is here, that is moving, right? So just if I ask you the magnitude of that velocity, that would be what? That this point is at a distance L1 from the axis being the z-axis here, and since this point lies on the joint, that would not be affected by the theta 2 dot velocity. This is just affected by theta 1 dot velocity, angular velocity. So only theta 1 dot contributes for the velocity here, and that is theta 1 dot L1, right? So theta 1 dot L1 perpendicular to this link will be the velocity. So let me draw it here. So it's basically L1 length, link moving with theta 1 dot, and your point is here P. So the velocity will be like this, theta 1 like this, right? This is the point 2 here. This is the magnitude of V22, right? Now now what remains is basically we have, so this is the velocity, and perpendicular to that just wait a second. Yeah, and our frame is basically aligned like this. So this is, we want to express this in the second frame. So our second frame is like this. This is link 2. This is a continuation of link 2, and this is theta 2. This is link 1. Okay, so this is theta 2. This is 90 minus theta 2. this is also theta 2. Okay, and this is that velocity v2. So you can then take components, that v2 c2 here, and this side it will be v2 s2 here. So on x it comes out to be v2 s2, on y of this frame it is v2 c2. So that's what it is written here. So theta dot 1 L1, that is v2 times s2, that is the velocity along the x direction of frame 2, and then theta 1 dot L1, that is again v2, and multiplying with c2, taking the cos component of it, gives us the velocity along the y direction of frame 2. So this is how v2 is being computed. Let me know if now it is clear, the calculation of v2. Yes, basically omega cross r, with omega being theta 1 dot and r being L1, right? Now you have to just take care that what frames are you writing it in, but the idea remains the same. It's omega cross r. If you write this in some other frame, then the actual components would change. So when you write the frame in which you express omega and r, that will basically govern what's the element, what are the actual elements that you are getting here. Otherwise the expression is correct. So just little bit of care needs to be taken about the frames in which we are expressing these velocities. We have expressed here in the frame 2, so that's why these components are here. Okay, so now we have the velocities, so it's time to write the kinetic energy. So kinetic energy in general of a rigid body can be written as half v m, or can be written as half m v dot v plus half omega I omega, right? Or in scalar terms it is half mv square plus half I omega square, right? So let's write that. So first let's write for link 1, that is ke1, link 1. So both links are have none of the links are going either pure translation or pure rotation. Both of them are going translation plus rotation. So this is the translation part of the kinetic energy, and this is the rotation part of the kinetic energy. So for link 1, the translation part of the kinetic energy is half m times the velocity of the center of mass, that is r1 times theta 1 dot square, right? So half m v c1 square plus the rotation part, so that is half I1, and the angular velocity of the first link is theta 1 dot, so theta 1 dot square. So for the first link it's very simple. It's because we know the velocity of the center of mass and the angular velocity. Now for the second link ke2, that is link 2, ke2 is equal to half. Now here what we need to write basically is v c2 square plus half I2 and omega of the second link, that is theta 1 dot plus theta 2 dot whole square, right? So that is omega 2, this is omega 1. Now let's put the value of Vc2. So Ke2 becomes, so what is Vc2? Vc2 we found out here, so we need to take square of this. Square of this would be uh, basically square of each of these terms and then add it. Okay, so first term is L1 S2 theta 1 dot. So just be patient and let's square it up and add them. So L1 square S2 square theta 1 dot square. Now in the second case there are two terms, so we'll use the formula a square plus b square plus 2ab. So first will be L1 square C2 square theta 1 dot square plus theta 1 dot plus theta 2 dot whole square R2 square plus 2 L1 R2 theta 1 dot plus theta 2 dot, right? 2 L1 R2 I think I missed something, that is C2 I missed, this is C2. So 2 L1 C2 R2 theta 1 dot plus theta 2 dot. Okay, now we can simplify this a bit, and this is plus half I2 theta 1 dot plus theta 2 dot the whole square. Now half M2, so these two terms can be simplified, because if we take L1 square theta 1 dot square common, so it is sine square theta 2 plus cos square theta 2, which is 1. So this just becomes directly L1 square theta 1 dot square plus R2 square theta 1 dot plus theta 2 dot square plus 2 L1 R2 C2 theta 1 dot plus theta 2 dot plus the other term. Okay, so this is what link 2. Now let's write the potential energy. P1. So P1 is M1 G R1 S1, because if you look at the diagram here R1 is the distance of center of mass from the origin and theta 1 is the angle, so R1 sine theta 1 is the height along the vertical axis, that is along the gravity. So M1G R1 MGH, and P2 is M2G L1 S1 plus R2 S12, this will be M2G. So the Lagrangian, that is Ke minus Pe, so that is Ke1 plus Ke2 minus P1 minus P2. So that will be the Lagrangian. So you can basically take in terms from here and fill it. So this is basically, if you write it completely, half m r1 square theta 1 dot square plus half I1 theta 1 dot square plus half, this will be m1, half m2 L1 square theta 1 dot square plus R2 square theta 1 dot plus theta 2 dot square plus 2 L1 R2 theta 1 dot C2 theta 1 dot plus theta 2 dot, like this, and plus half I2 theta 1 dot plus theta 2 dot square, and minus m1 g r1 s1 minus m2 g l1 s1 plus r2 s12. This is the total Lagrangian. Now we'll start taking the derivatives. So first is del L by del theta 1. Now this you should verify from the lecture slides if the expressions are correct. M2G L1 C1 plus R2 C12 and del L by del theta 2 is M2 L1 R2 S2 theta 1 dot So this I have written from my notes. I'm not calculating it right now because that will take much time. So just take a few minutes, and if you can just verify either of these expressions uh, so that we know that we are on the right track. We have to be a little bit careful while taking these derivatives regarding the dependencies of theta 1 and theta 2. Okay, so let's move on and write the derivatives with respect to the velocities. So del L by del theta 1 dot is equal to, this is slightly longish expression, so bear with me. So this is del L by del theta 1, and similarly we can take differentiation with respect to theta 2 dot to finally get this I2 plus M2 R2 square plus M2 L1 R2 C2 theta 1 dot plus I2 plus M2 R2 square theta 2 dot. The expression for L is this. I think I made it slightly dirty here. This 2L1 R2 yeah 2L1 R2 theta 1 dot C2 theta 1 dot plus theta 2 dot. So this is the expression for L. Once you have the expression for L, it's mostly the task of having patience and doing the derivatives carefully so that you don't make any mistakes. Okay, so we have all the four quantities that we need in order to evaluate the Euler-Lagrange equations. So for joint 1, I can show for first joint, or let's say I can show for second joint, and maybe you can repeat the process for the other joint. So it will be d by dt del L by del theta 2 dot minus del L by del theta 2 equal to tau 2. So we have to, so this is the expression for del L by del theta 2 dot, and we have to take the derivative of this expression. So let's first write the first term. So we'll take derivative of this expression. So the quantities, this is a constant, and this has a theta dependence, so this needs to be differentiated. So first we'll use the chain rule. First we'll take this entire expression in brackets as constant and differentiate this, that is theta 1 double dot, and then we will take this as constant and differentiate this term. So first is I2 plus M2 R2 square plus M2 L1 R2 C2, and then theta 1 double dot plus, now we will differentiate the expression in the brackets. So the first two terms are constant, and then we will have minus M2 L1 R2 S2 theta 2 dot and multiplied with theta 1 dot, right? This is the term. And then for the second term we have no dependence on theta inside the for the term in the brackets. So see the theta 2 double dot, this is the derivative. Just have a quick check, you guys can do. Okay, so the other term is del L by del theta 2, which I can just rewrite down again. Del L by del theta 2 is equal to minus M2 L1 R2 S2 theta 1 dot plus theta 2 dot minus M2 G R2 C12. Okay, so finally what we will write is tau 2, we use a different ink, so tau 2 is equal to I2 plus M2 R2 square plus M2 L1 R2 C2 theta 1 double dot, then we have I2 plus M2 R2 square theta 2 double dot, then we have a term minus, I think I should continue here, so minus M2 L1 R2 S2 theta 1 dot theta 2 dot, then I have plus M2 L1 R2 S2 theta 1 dot square, then I have plus M2 L1 R2 S2 theta 1 dot theta 2 dot and finally M2G R2C12, right? Now the nature of this expression, even though I've written it for just tau 2, we can get all the insights that we want regarding the equation of motion for a rigid multi-body system. So uh, basically what you see here is that is that first, so tau 2, so first we have terms that are related to the double derivatives, right? Then we have terms that contain squares of the velocities, and or quadratic terms, basically quadratic terms. And finally we have a term which has gravity in it, right? So this is the structure, this is the term having the so this is the term having the double dot, right? Then we have terms having these quadratic terms, right? And finally we have term having this gravity. This is the insight that we want to have for the equation of motion. So now what I will do is uh, rather than deriving the equation for the first joint, which you can do on your own, and then writing both the equations together in a matrix form, if you do that, so if find tau 1 and write tau is equal to tau 1 tau 2 is equal to a matrix equation, then that equation looks something like this. So m q q double dot plus c q dot into q dot plus gq is equal to tau. So tau is this vector tau 1 tau 2. For 2r case, this will be theta 1 theta 2, and similarly its derivatives. So first this is called the mass matrix, or to be more precise, joint space inertia matrix. This is what is known as the non-linear effects matrix. This has the Coriolis and centrifugal terms, and this has the gravity effect. This has the gravity terms, and this is the joint torques. All right. So going back to our equation that we found out. So we have these terms which are the q double dot terms. Then we have these terms which basically, this is the centrifugal term, and terms like these are Coriolis terms. And finally we have some theta dependent terms multiplied with the gravity, right? So the equation of motion of a rigid body that involves terms like I alpha, so this is equal to I alpha terms, right? So if you try to relate, then these are the I alpha kind of terms. Then this is your omega cross r terms, centrifugal terms, and this is your omega cross v terms, right, which is basically our Coriolis term. So, and this expression is very general and powerful. So this is for like whichever system satisfy our initial two assumptions basically. So for any ideal rigid multi-body system, this is the equation of motion. Okay, this is the equation of motion. Now we can add two we can look more closely into these terms and maybe some comments about these matrices. So first is that this matrix MQ, that is the joint space inertia matrix, joint space inertia matrix. Now as you would guess, since it is related to mass and inertia, this is a symmetric positive definite matrix. Alright, this is always a symmetric positive definite matrix. So a very good check, if you let's say compute mass matrix numerically or using some program that you have written, then you must check that mass matrix that you have, the expression for mass matrix that you have generated. If you evaluate it at some theta 1 theta 2, then the eigenvalues of that matrix should come out to be positive, because positive definite matrix have positive eigenvalues. Now the CQ, this has all quadratic terms, and together called as the, as I mentioned, non-linear effects. And finally, this is the effect of gravity, and it has as as predicted, this has no dependence on velocity. Okay, now the kinetic energy of the system can be represented as half q dot transpose mq q dot. This is the kinetic energy of the system. So once we write the once we know this relation, so if we know this relation, what we can do is basically we have the q, right? So here we calculated the kinetic energy, right? The total kinetic energy we calculated, right? Ke2 and Ke1. If we just take double derivative of that Ke expression with respect to Q dot, then we will get the mass matrix, right? So what we have is that the elements of the mass matrix Mij are basically del 2, and if this is the kinetic energy expression, then del Qi del Qj. Okay, so this is how, for if we just need to calculate the mass matrix, not the entire equation of motion, then we can just compute the kinetic energy and take the Hessian of it. This is called the Hessian operator. Basically it's double differentiation with respect to Q dot. Yeah, here it should be Q dot. So that will give us the mass matrix right away. No need to calculate the potential energy and do all the derive the equation of motion. Okay, now the other is that GQ is basically minus del PE by del Q. Okay, this is how G can be computed. So if we just need G, we can just take gradient of potential energy, okay, with respect to, so if we differentiate the potential energy expression with respect to Q, the joint positions, then we will get the expression of G. For the nonlinear effects, it's not so straightforward, so it has a kind of a more complicated expression. So that is given by so that is computed at the very end or after computing of the mass matrix, because then we can compute it like this. So these expressions that I'm writing, that they are helpful if once you want to code this, as I described, that this is not very, for 2R you can still do it with hand, but for 3R and for more complicated systems and complicated robots, it won't be feasible to do it with hand. It will be very error prone and tedious. So we will use MATLAB and tools like that, and there we can directly use these expressions to find out the mass matrix, the gravity terms, and the nonlinear effects vector. If there are any doubts here, then please let me know. So what we have seen is that using the energy based Lagrangian approach, we can compute the equation of motion of an ideal rigid multibody system. The equation of motion can be represented like this, that is mq double dot plus cq dot plus g, where m is the joint space inertia matrix. It is an n cross n where n is the degrees of freedom of the system. So n cross n symmetric positive definite matrix. Its eigenvalue is always positive. C is a term which contains quadratic terms, that is either q dot square, qi dot square, or q dot I times q dot j. And finally gq is the gravity term, so it does not have any dependency on the velocities, and tau is the joint torques. And this is how we can compute the individual matrices. Now for any system, let's say we have all these matrices and we have them as functions which we can evaluate. So now there are two problems, just as in kinematics, and this we have mentioned before also. We have the inverse problem, so the inverse dynamics, and the forward dynamics. So inverse dynamics, we know tau, we compute q double dot. No, sorry, this is inverse, this is not inverse dynamics. I again mixed it up. Yeah, inverse dynamics means to know the cause. We have the effect, that is the accelerations and positions and velocities, and then we want to know the effect, that what caused this acceleration. So we know q double dot, q dot q, then compute tau, and in reverse we know tau, then compute q double dot, and then from that we get q dot, from that we get q. So this is the forward dynamics equation. So generally forward dynamics, as you can see, this involves integration, and this is just like matrix inversion and matrix multiplication. So this is not very tricky, especially for manipulators. Inverse dynamics is pretty straightforward because we compute all these terms and we just add it up. So now the last thing that we will touch upon today is basically rewriting this joint space equation of motion into Cartesian space or the operational space. So the joint space EOM is what we just derived, that MQ double dot plus CQ dot plus G is equal to tau. Now many times it is useful, especially doing impedance control and other control algorithms. We want to express everything in Cartesian or operational space, EOM. So the first thing that we know is that tau is equal to J transpose F, right? So that is the first relation. So what we can do is MQ double dot plus CQ dot plus G is equal to J transpose F. Now we also know that X dot is equal to JQ dot and X double dot is J dot Q dot plus JQ double dot. So using these relations we can put here, so it will be M Q dot will be X double dot so from this expression Q double dot is X double dot minus J dot Q dot and J inverse, right? So it will be M J inverse x double dot minus j q dot, sorry, j dot q dot, right, plus c, then q dot is again j inverse x dot plus g is equal to j transpose f. Then here we can write m j inverse x double dot and then we can write this term is as minus m j inverse j dot, and q dot is again j inverse x dot, right? So this j dot q dot is now j dot times q dot is j inverse, from this relation q dot is j inverse x dot, so that is what we have written. We have opened the bracket, right? And then cj inverse x dot plus g, right, plus g. So if we again try to bring it in the same form as the joint space equation in terms of just x dot now, so it will be m j inverse x double dot plus cj inverse minus m j inverse j dot j inverse m j inverse j dot j inverse, and that is multiplied with x dot plus g is equal to j transpose f. And then we can just bring this j inverse of j transpose this side, so it will be minus j transpose t m j inverse x double dot plus again j transpose inverse cj inverse minus mj inverse j dot j inverse x dot and plus j inverse t g, that is equal to f, right? So now we can write this as the Cartesian space mass matrix, this entire thing as the Cartesian space Coriolis matrix, and this as the Cartesian space gravity terms, right? So finally it would be mx x double dot plus cx x dot plus gx is equal to f, So this is the Cartesian space EOM. All right, any doubts in this? Yes, definitely there is a terminology for it. So the most appropriate term for it is taken from the analytical mechanics literature. So Q is generally called the generalized coordinates or generalized positions, and its derivatives are called similarly. Q dot is generalized velocity, Q double dot is generalized acceleration, and tau is generalized forces. So remember that this 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 generalized, this type of nomenclature does not take any assumption of whether the uh, whether the joints are revolute, prismatic, or any assumption on the nature of the joints. This is the, like I can say, the most general nomenclature. Once if you're working with systems which have only revolute joints, then these uh, for simplicity these terms are called as joint. Q will be called as joint positions, q dot joint velocities, q double dot as uh, joint acceleration, and tau as joint torques. So for a manipulator, uh, the more convenient set of terms would be joint position, joint velocity, joint acceleration, and joint torques. Okay, so now I'll just quickly summarize what we have discussed today. So the objective today was to basically understand how do we relate the forces to the motion. So how do we basically derive the equation of motion of a system? And there are two ways to do that. One is the energy based method, that is the Lagrangian approach. Another is the force based method, that is the Newton Euler approach. uh, in the process of finding dynamics, the first step is to know about the dynamical properties of the system, and inertia matrix is one part of it. Inertia matrix is a 3 by 3 matrix which is positive, definite, and symmetric always. uh, its terms can be calculated as follows, as shown here. The inertia matrix can be represented in its principal axis, which correspond to the eigenvectors of the inertia matrix, and the eigenvalues correspond to the principal moments of inertia, the three values I11, I22, I33. Now for the equation of motion, for using Lagrangian formulation, what we need to compute is first the velocity propagation, to know the angular velocity and velocity of each link, such that we can write the kinetic energy of the entire system and the potential energy of the entire system. Once we know the kinetic and potential energy, we write Lagrangian of the system, and that is defined as kinetic energy minus potential energy, Ke minus Pe. And once that is correctly written, there is a very systematic procedure to write down the equation of motion, or the derive the equation of motion using the Euler-Lagrange equation. So basically this equation is written for each of the n degrees of freedom of the system. So if there are 3 degrees of freedom, then 3 times this process would be followed. That is d by dt del L by del Qi dot minus del L by del Qi is equal to joint torque. So this, all these steps are summarized here. And after writing the equation of motion, we for 2R manipulator, we saw that there is a specific pattern of terms that are appearing in the equation of motion, and when we write it for all the joints and basically group all the terms, we get the equation of motion in this form, which is mq double dot plus cq dot plus gq is equal to tau, where m is the joint space inertia matrix, uh, C is the matrix having the nonlinear effects, the Coriolis and centrifugal effects, and G is the gravity term. So uh, this is the structure of the equation of motion, not only for serial, for manipulators, but for any ideal rigid multi-body system. This is the structure of the equation of motion. Finally, in practice, getting these or deriving the equation of motion is a tedious and painstaking task for larger systems, for more degrees of freedom. Uh, let's say we want to do it for actual full robots, let's say a legged robot, like a quadruped or a humanoid or maybe even a 7 degree of freedom arm. So there it is not feasible to do it by hand. So we need we need to use efficient implementations that compute these dynamical matrices. uh, we can do it. A crude implementation can be done very easily on our own by using these expressions. uh, so mass matrix can be computed by taking the Hessian of the kinetic energy. The gravity terms can be computed by taking the gradient of the potential energy, and the Coriolis matrix can be computed by further differentiating uh, the elements of the mass matrix as shown here. So that will give us all the dynamical matrices that are needed to write the equation of motion. And finally, once we have the equation of motion of the system, we can solve both the inverse dynamics problem and the forward dynamics problem. So for the inverse dynamics problem, we know the accelerations, velocities, and positions, and we compute the torque that is causing that motion. And for the forward dynamics motion, we know the torque, but then we compute the accelerations and then integrate the differential equation to compute the velocities and the positions. Finally, the equation that we derived is written in the joint space because the variables are q dot, q double dot, and q. If you want to write it in the Cartesian space, where the variables are, let's say, the end effector position, end effector velocity, and end effector acceleration, that is the operational space. So then we can use these transformation that is based on the Jacobian to get the Cartesian space or the operational space equation of motion. So this is where I will conclude for today's discussion hour, and in the next discussion hour we will see how we can arrive at the same equation of motion using the Newton-Euler approach, and then we'll solve some problems around these concepts. So thank you for joining, and I will see you in the next discussion hour.